little brief history of what General Kinematics is we're a privately held company. We're located in Crystal Lake, Illinois. On the picture that I have up at this time is our manufacturing plant, sales, engineering, all the above. We've been in operation we're in our 61st year right now. And I have been with the company for coming up on 45 of those 61 years. So the thing that kind of getting us into what the topic is going to be today with the brute force versus two mass is that the mining market has grown. Everything's larger, everything's higher capacity. As you can see, some of the write-up I have up, everybody's looking to do higher tonnages, more throughput, bigger equipment. They want to utilize less machines in a lot of situations. And that's where we're going to get into these different machines and what they can and can't do. And so we'll hit that here shortly. Brute force, everybody that's familiar with screening currently in the industry is most likely very familiar with brute force. It is a machine that the drive force, whether it be a drive shaft, a offset weighted shaft, a motor, whatever it is attached directly to the carrying surface for the material flow. It is driven by pure horsepower. It is very simplistic in design, has isolation springs to keep it, so that when it vibrates on top of the foundation, that it, absorbs some of those forces, but not all. But it is a very simplistic way of handling material. And it's one of the two methods. Just so you know, we make vibratory equipment. Our company does. That's what I spent 30 years designing these before I moved into the sales role. And we make both brute force and two mass. So we don't have one that, that is light years above the other, but we do prefer one in certain situations and a different one in other situations. Two mass is a little bit different, and I'll show you here a picture in a second. Two mass, it has the same isolation springs as you would see in a brute force machine. It has the carrying surface, which in the picture in the lower right-hand corner is designated as MT. That's a mass trough, and above that you'll see some springs and then a mass exciter. And that's what we attach the drive force to in this application. So the drive is actually, whether it be a motor or a shaft, it's attached to that upper mass, and it has the springs in between the two different masses. They'll vibrate opposite each other. As one goes up, the other goes down, and vice versa as they come together and go apart from each other. And it's a much different approach than the brute force machine, a little bit more complicated, but we'll show you some of the pluses of doing this type of design. Here's some pictures. This will actually kind of make it a little bit better to understand. If you look at the picture on the left is a typical banana screen, which a lot of people I'm sure have seen at one time or another in their careers. And the drive force up on top, drive FB in this picture, it's attached directly to the carrying surface, and it moves in a circular motion with respect to the machine, and it makes the machine vibrate, and it'll move material. The picture on the right has actually the springs in between the two masses, the upper and lower. So you can see the carrying surface down on the bottom where it's designated trough material or MT. You have the reactor spring system in between mass 1 and mass 2. And in this application, the motors are actually attached directly to that upper mass. There is no shaft or drive belt or anything that attaches it. The motor actually goes for a ride. It sits on that upper mass and will vibrate as the machine vibrates. Oh, let me get over. I don't know if you can hear me very well right now. These are just two. This is showing the difference of brute force and two mass, one to the other. Kind of breaking down the components so you can see them. And here, this is a two mass design on the top and a brute force on the bottom. Here's your springs in between the two masses. This is a much smaller machine, makes it more simplistic. And again, the drive is attached directly to the material surface. And what you're going to see here is you're going to see how they react to material flow, one versus the other. As we increase the material loading or go with a deeper bed depth, the material flow changes. You don't want to stay on that too long because it's probably hard to hear me when that is on. But the brute force that you saw in the pictures that we were showing, it actually works inversely of two mass. A brute force machine, as you add material load to it, actually will decrease in amplification. The stroke will go down. On a two mass resonant natural frequencies design, it'll actually increase in stroke amplification. So therefore, it can handle a much deeper, heavier material load and respond. It'll actually respond in a positive manner to material loading, where brute force will respond in a negative direction. You can see in the equations on the left, brute force is very, very simplistic. It's wheel force, or which will actually convert into horsepower in this case, or centrifugal force, is equal to half the stroke times the mass. So that's very, very simple. Wheel force is constant. It never changes. You put that on your shaft or you put that on your motor. It is always constant through the application. Mass will change. You're going to go from an empty condition to a loaded condition to an overloaded condition. I'm sure any of you who have been to a facility that's got a sag mill, and they'll burp every now and then, or overload the machine downstream, and they'll hit it with a very heavy burden occasionally. Well, when you have a brute force machine, it'll actually bury the machine in a lot of cases. It'll actually drive the stroke so low that it cannot handle anymore. So your stroke goes down as mass goes up because of the constant wheel force. Pardon me? Did you say something? Heidi?
No, I think somebody just accidentally unmuted themselves. Please continue.
Oh, okay. I'm sorry. The two mass frequency equation is a much simplified version. Well, here, let me show you the brute force. Show you real quick. If you change the weight and you put 30,000 pounds in there, and you're targeting a half-inch stroke, as you change that to 40,000 pounds, the stroke drops. Again, because the wheel force is a constant, it cannot change, so it cannot react to it. The stroke continues to go down as you increase material load. On a 2-mass design, K is the spring rate. That's the springs that are between mass 1 and mass 2. That, in this case, is the constant. You don't add or subtract springs as the machine's running. They're always in there. You put 100 springs in that, it's going to stay at 100 springs. The mass, again, can increase just as it does in a brute force application. In this case, what you're changing isn't the stroke, you're changing the frequency. So in this case, the frequency goes down. A little bit better formula as to what it really is doing within those numbers. So it was simplified above. And I'll show you in the next graph coming up here. But here, if you do the same thing where you apply the 30,000 pounds and you're solving for the RPM or the speed that the machine's going to run at. This is actually the natural frequency. I apologize. The machine in this case might be running at 900 RPM, but the natural frequency is 1,050 with 30,000 pounds on it. And you increase that to 40,000 pounds and the natural frequency drops. Again, at 50,000, it drops again. Now you can change how quickly that reacts or how slowly that reacts by doing several things. By changing the amount of springs, wheel force, all sorts of different variables. But let me show you here in the graph. Brute force operating frequency. The machine's running at 900. You're targeting in this case just over 0.35, so say 3/8 of an inch stroke. Unloaded condition. Wheel force constant. You increase the mass, the stroke goes down. That happens on every single brute force machine that exists on the planet Earth. So on the 2-mass natural frequency design, again, we're operating at 900 RPM. Probably a lot of you are familiar with the bell curve. This is where we run our frequency. By changing the quantity of springs, changes the frequency in the machine. So we set our frequency to be above running speed. So in this case, we're at 900 RPM on the motor. We put our frequency up at, say, 1,050. As we increase mass, it shifts the bell curve to the left. As it shifts the bell curve to the left, the stroke will actually increase. It's a good thing from the standpoint that it does not bury itself. It will actually unbury or actually get rid of material quicker. If you have a upset condition or an overload condition, it'll get rid of the material quicker by a long shot than a brute force machine will. It will not allow itself to become buried. And it's responsive to material loading, which is a great plus in most conditions. Sorry. Here's a brute force screen. And normal during startup mode. And you see as it's ramping up to speed, you'll see certain things happen. These have large motors. They have large eccentric weights. They have tremendous stresses during startup. So that all goes back in through the drive tube in this case, or drive shaft, depending on what they have going through the machine for their drive forces, and through the isolation supports. Those are the only connections. You got 2 connections to earth, and then you got where the drive attaches. And that is it. So as it's ramping up and ramping down from running, it goes through isolation frequency. Typically, an isolation frequency is down very low. It's somewhere between 150 cycles and 100 and 200 cycles normally, depending on how soft you make your springs. And it'll It's not as bad a condition at startup because typically you're able to pull the motors up quick enough to get through it fairly quick. You'll see some of these stresses at startup, but you see much, much higher stresses at shutdown. And that's when you'll see the machine bouncing and twisting and turning, and then it can potentially cause damage to the machine. Especially if it's done quite frequently. If you're starting and stopping it quite often, you'll see the stresses occur on a much younger machine. Here's a 2-mast machine. You can see that it's relatively quiet, and they're shutting down the machine. You see the wheels coming to a stop. And you'll see very little motion in the machine. The biggest difference you see, with those is the size of the wheels that are used. When you have a brute force application, you're using very, very large eccentric wheels for offset weight. On a 2-mast natural frequency, because you're using the frequency to actually amplify your stroke, you use very small wheels. So it does several things. It actually allows you to start up and shut down much, much easier on a 2-mast because you don't have that wheel force that's required to start and stop. You can even plug stop or DC brake a 2-mast machine, which there's no way you'd be able to do on a 2-mast because of the size of the wheel, or on a brute force, sorry, because of the size of the wheels are enormous. So typically you couldn't do it. It would not allow it to stop. Here's a typical brute force banana screen. And this is what you see if you look at a side elevation of a brute force machine. You'll see an elliptical stroke, and that's because you have a drive force that's attached at one location and is spinning in a circular motion. So you won't just see a direct line of action. I don't know if you can see my mouse. You will not see it vibrate just straight up and down. You'll actually see an elliptical motion. And it's different. On the feed end, you'll see a forward throw. The motor area, you see almost circular. You'll see a little bit of an elliptical shape. And then at the discharge end, you'll see a very elliptical shape, actually reversing. So when you see material flow on a machine like this, it actually, and because also the deck inclination is very, very steep on a banana screen at the feed end, material will blast through that area very, very rapidly. It'll because of the stroke is all forcing it downstream, is trying to evacuate the feed end of the machine. It'll shoot down that first third to half of the machine very rapidly because of the stroke and the angle of inclination. Once it hits the end of it, the discharge end of it, it will slow down dramatically. And I actually have a real life video where I'll show that happen. And so all your screening, when you're moving as rapidly as they move at the feed end and middle of the unit, you cannot get as effective screening on that machine because the material is just shooting past it very, very quickly. And so you need time. When you're going to screen material, you need time to do that. It has to work its way through the bed depth, and it has to work its way through the deck at that point. So you can see how the machine runs in that circular elliptical type motion. So you have high velocity in the feed end and low velocity at the discharge end. You get into here's the comparison. You look at the difference in tonnages and difference in time on the machine. You see how steep a banana screen slope is and how rapidly that material moves at the feed end. And then look how slow it is at the discharge end. Here's an install that we have up in Canada that actually is a sag mill discharge screen. And it's consistent and linear down the full length. The stroke that you see and the angle that it's stroking at is exactly the same no matter where you take that reading. It's the feed in, the middle, the discharge, it's exactly the same. If it's 1/2 inch we're targeting, it's 1/2 inch everywhere. If it's 3/8, it's 3/8 everywhere. One thing we actually did is we actually put a camera underneath the machine on the right in this video, and actually all the water was gone from the material at about the midpoint or halfway down the unit. Here it shows the retention time is over twice as long on the 2-mass than it is on the banana screen. And that can vary from manufacturer to manufacturer, and that can vary, depending on how you design the machine. So not only will you get more effective screening, but you're also going to get more effective handling of the material. It'll be constant, even. Play this real quick. Oh, I'm sorry. I apologize for that. So you're seeing two different things happen here. 2-mass sub-resonant design, distinctly different from conventional screening. And I'm sure you all agree that it is very different. It's unique. And it's increased the reliability, the uptime, much, much lower power requirements on a 2-mass than on a brute force. As I said earlier, brute force requires pure horsepower. If it takes 50 horsepower to start it, it takes 50 horsepower to keep it running at all times that it's running. It never changes. That horsepower requirement never changes, irregardless of how much material you put on it. So if it's 50 to start, it's 50 all the time. 2-mass design actually takes a certain horsepower to start, and then that drops off as it gets up to running at speed, and the frequencies are all designed properly. It might take 50 horsepower to start and only 20 horsepower to keep running. And it's that natural frequency design that allows that to happen. So your power consumption drops off dramatically once it's up to speed and running. And they come up to speed very quickly. It's much smoother startup shutdowns, as you saw in the video. We're able to actually make wider machines because of the inherent stresses are much, much lower than you'll see in a brute force style machine, and they're material responsive. You can get them in. I'll shoot through some of these real quick. You can get the single, double cascading decks. You can get them in any size, shape. If you want a double or triple deck, you can do that. You can, the water manifolds can actually go right through the body of the machine. They do not have to be separate and held above. You could put one on a lower deck by going right through the wall of the machine. There's no stresses to worry about. We're not concerned with that. And we've actually put pipes right through the side of our machine before, and it's working very, very well. We handle the material on a 2-mass machine 3 to 4 times longer than a typical brute force machine. Brute force is usually 7-8 seconds. That material's on, off. And we'll see in the neighborhood of 30 seconds, 35 seconds on a 2-mass. Again, you can change that somewhat, and you can design it slightly different. The brute or the 2-mass machine in our particular design actually has a center spline to it. What that center spline does is it enables you to take the machine apart in the middle if you so choose. It makes it much easier for container shipping from one location to another. It makes it easier for truck shipping on a very wide unit. If you send out a unit that's 3.6 meters wide, that's too wide for the roads. It's all permitted. It's huge. So we'll actually send it out in two halves, the left half and the right half. And it also helps decrease your stresses dramatically. So the stresses on that style design, the bottom design you see on the left has a center spline where the top left does not. So the bottom left actually will be much lower stresses than you'll see in the one on the top. Here's a direct comparison, 2-mass brute force, positive response to material load, negative response to material load. Again, like I said at the very beginning, we make both designs. And we find for different industries, mining being one of them, the 2-mass definitely does a much better job. At least that's our feeling, and that's what we have seen at many, many locations. The retention time, stratification is much better. Dewatering of the material is much better. Much smaller motors, much smaller wheel force requirement. The longevity of the equipment is exceptional. And I'll show you some of those here very shortly. And, you know, if you look at the brute force, you know, they have very short retention times. They have that oil bath you got to worry about for the drives. On some of them, not all of them are designed that way. It takes large motors, large eccentric wheels, you know, to operate a machine of that size. I want to show you a slide. This is from actually from that application we've got that was up in Canada. I showed you a little video on earlier. And if you look at the red line, that's a SAG mill total feed. So that includes the recirculation loop and it includes their fresh feed. The fresh feed is that light, almost like pink colored line on there. And they are all over the map. So they are feeding material to the machine up and down and all over the place. It's anywhere from 2,300 tons per hour all the way down to 1,200 tons per hour and back and forth. And if you look at the blue line, the dark blue line, that is the total stroke of our machine. It is very consistent all the way down through the gamut. So it's reacting to that material load. This is proof of it. These are stroke monitors that we have on the machine, and it holds its stroke exceptionally well. And it just, no matter what the material load is going to it, it will adjust and handle that. That's your capacity. That's your trough stroke, and then the blue line, dark blue line up above, is the total stroke. That's the exciter and trough. Again, here, this one's really up and down.